and what were the conveniences of the systems. We were experts of that. We were handling the system for many years, so it was quite stable, I would say. I will also explain a little bit of what California ISO does. That's my job from last 8 years. What are the responsibilities and what is the role in Western American electrical grid, and what are other key players. And electricity is a regulated commodity. It is governed heavily by the policies that govern that government is passing. So as any operator, we are doing what we are given the constraints of the government policies. So I'll briefly touch that. And then the rise of the renewables. In last 20 years, we have seen a lot of wind and solar got integrated in the power grid. And this is basically due to the policies that the government is passing through from last 20 years. And EV is also a result of the same policies. The challenges that we faced in the renewable, they are very related to the EV. EV, as I said, is nothing but an extension of all the policies that we had from the government. And again, the same government is incentivizing the EV vehicles, and that's why we have a surge of EV vehicles in last 5 years. And the problems are similar, a little bit different, but almost on the same lines. One problem which is unique to EV vehicles is they are charging and at ad hoc basis. Anytime a car can be charging at any location, which is different than a conventional system and a renewable solar top or solar power plant or a wind power plant, because all those were stationary. Now we have a moving piece for the EV like electrical vehicles. Then I think I'll combine everything, and then we'll see how it is impacting the power balance and what utilities are doing right now to mitigate it. We don't have very big problem right now because it's only 5% of the cars are electric. But going forward with the policies that government is making, in maybe 10 to 20 years, we will have all the cars which are electric. And we might have 30% more load in the system, which is variable. So we have to prepare for that. So there is a lot of research going on, and even government is funding a lot of research, and all these utilities are coming together and preparing the infrastructure, preparing the technology. And I will briefly touch upon that also. So that was the agenda. Now let's discuss our conventional electricity grid. Imagine this is 2000 and how any electricity grid across the world would be operating. We'll have a power plant somewhere where we will be generating electricity at around 33 kilowatt and kilovolt, and then we're going to step it up with transformer. Then we're going to transmit the power, and then we'll go to the distribution system. We'll step it down. There'll be 3-phase line in the transmission system. There'll be single-phase line in the distribution network, and in our houses, we'll get the electricity. Conventionally, we have 3 types of loads. We have industrial load, we have commercial loads, and we have residential loads. So industrial loads, as you know, they are big loads, heavy loads. They are operating during the daytime. Same with commercial loads. They are the offices and the shops, big units, right now even malls. So they are also have, morning hours and the evening hours. That's where most of the, during the daytime from 8 to 5 p.m. That's where many commercial load will have a high requirement. Then there is a residential load. Residential load requirement is a little bit different than commercial. We have a peak in the morning and peak in the evening through the night. And then after midnight, most of the load is settled. It's just base load that we have to meet the requirement for. And it's around 60% of what it is in the daytime. Back to the conventional generators. Back in the 2000s, we'll have around 80 to 90% generation coming from nuclear. Nuclear used to be, and this I'm talking mainly for California, because that's where my experience is and that's where my whole case study is going to be based. So we used to have around 20% nuclear, around 40% coal generated, and 30% roughly natural gas, and the remaining 7% hydro generation. And then there was negligible solar and wind at that time. There were still challenges at that time. The transmission system that I was talking about between the generator and the load, it's very expensive. It's a 3-phase system, and we have a lot of losses. That's why we are stepping up after the generator and stepping down when we are about to serve the load to minimize the losses. We also created DC lines to minimize the losses. That was an invention around that time. And overall, the infrastructure was the problem at that time than the technology. With that given system, I think we were quite mature in doing the power balance, but the downside was that there was high carbon emission. All the generators that we used to have mostly were coal or natural gas. And as you know, there is a high carbon dioxide, CO2 emission and GHG, the greenhouse effect. And lately, the surge of global warming and reducing the pollution created the need of renewable. I think I'll talk more later on in my presentation, but right now I want you to understand this conventional system before we go deeper into the complexity of the system. Next, I want to also touch briefly on the load profile. As I said, night we used to have very less load, and morning peaks used to generally 6 o'clock. People will rise up, they will get ready to go to offices. Some will reach to office 7, 8. That's where the morning peak comes. So if you see in the morning, that's where most of the residential and some of the commercial load will start. Then it used to be flat around the afternoon, because whatever has to be started up, all the lights are up, all the industries are up. So it used to be quite flat. It is much higher than the morning, but it used to be still almost flat till the evening, where again the residential load starts increasing and some of the commercial and industrial is still on. So we can have this evening peak used to be where we need the maximum energy at any point. So we used to have natural gas generator, which used to help in this time, and hydro generators. So I think I won't assume that you know the profiling. Getting back to the type of generators that I have, nuclear is a generator which is always on. Coal is also almost on. There are few generators which takes around 10 hours to start. So we're not going to turn it on and off. There are some still generators which takes around 6 hours to start. So that we can turn off in the night, and in the morning I can turn it on again. The generators which gives me a room to move a little bit is the natural gas and hydro. Hydro is very fast. I can open up the gates for the water, and within 1 minute, 30 seconds, 1 minute or 30 seconds, I'm going to have a power generator from the wind turbine, from the hydro turbine. So those generally are used for peakers. And if you see the evening peak, that's where most of my hydro used to be very useful, because within 1 minute, I can turn on the plant and I can get around 1,000 or 2,000 megawatt right away. The other best option we used to have at that time was the natural gas. Natural gas takes somewhere around 30 minutes to 45 minutes, 1 hour to start. So in the market, we do forward-looking market. So we look into the data of right now, and we take a decision 1 hour from now. So we know what's going to happen at 6 o'clock, sitting at 3 o'clock. So if there is a need, we can always start up a natural gas plant, and we can meet this peak. So, so far, is it okay? I hope there is no questions. Hello.
Okay,
Shreyas, you can. Okay, good. I'll keep on checking because I was told there was some technological issues in some other presentation. So bear with me with that. So, so I think this is the load profile, and those were our challenges at that time. Morning peak was a little bit problem, evening peak was a little bit problem, but we figured out the ways. The maximum variation we used to have between the day and night used to be around 8,000 megawatt, but that can be easily taken care by the hydros we had and the natural gas we had. Just to give you an example, we have a lot of hydro in California. The biggest hydro plant in California is around 1,000 megawatt. So just turning on one plant, I can get 1,000 megawatt, which can take care of this peak most of the time. And I have three such generators, around 350 each. They come in handy during the evening. So we walk through the normal generators, we walk through the load, everything is good. But then these are the players that I want to talk about. In America, we have a lot of different bodies which take part in any decision which happens for any state or even any city. So I'll talk first about FERC, that's Federal Energy Regulatory Commission. So that's a US federal agency that regulates the transmission and the wholesale of electricity and natural gas. So it's a federal agency. The ultimate head of this agency is the President of America. President of America will have will appoint a president for FERC, and they will come up with any policies that is needed for electricity and natural gas throughout the country. Then we have also one more national level contributor, which is North American Electrical Reliability Corporation. So their main focus is to assure that there is an effective and efficient regulation of electricity. So everyone is following the correct policy. Like if you're an operator in a control room when you're sitting for any utility, what kind of decisions you will take in certain circumstances, that's all written in a procedure. So there are some authority that you have sitting in control room and some you don't have. So everything is NERC certified when you're sitting in control room and you're taking decision. You cannot just turn a power plant on if it is not certified and if it's not a policy and a procedure given by NERC. Then I'll come to state level players. We have CEC. It's California Energy Commission. They are the policy makers for California. So the ultimate boss of CEC is the governor of California. They study what is required in energy for the whole state, and they come up with policies. So back in 2011, they created a policy that everyone in the state, if you're making a new house, you have to have a rooftop. So they just sign off, and then every builder has to follow that. Then comes ISO. That's where I work, and that's where most of my experience is coming from. So when I'll be talking, I can tell what other entity can do, but my main focus of work has been ISO from last 1 decade. So California ISO's main focus is to manage the flow of electricity on power lines, manage the wholesale energy market, and see any infrastructure planning. So what is infrastructure planning? That if any generator has to be built up, it takes so many years to build a nuclear plant or a thermal plant. So we do studies. So there is a separate department which will do the study that where a generator is needed, what is the rating, if it is needed or if it's not needed. There are a lot of private utilities which come up and say that we want to build up a generator. But if it is not needed, it will not be approved by ISO. So you can't just construct a generator and start producing electricity to the grid. Lately, ISO also has one more responsibility added in last 1 or 2 years, that is reliability coordinator. So we used to take care of the market. Market means at any point of time, everyone should get electricity at the most economical rate. So we run optimizations every 5 minutes, and we tell which generator should be running at point. So we run a day ahead market where we tell a day advance, like all those big coal thermal plants that I talked about. You need around 12 hours of time, notification time. So we tell them a day before that you have to tomorrow at 6 a.m. you should be on. So they get prepared, they buy natural gas, and they will be ready to produce the electricity when we tell them. We also tell them 4 hours in advance. We tell them 1 hour 45 minutes in advance, and then in the end, in 7 minutes in advance, we tell them exactly where they have to be. For a generator, one thing is that they have to be on, and second thing is at what level. So we tell them how much electricity they have to produce at any point of time. So this is the granularity that we have control on any generator throughout the state. So I think this I just wanted to quickly go through so that you know where I'm coming from, what can be the challenges. So this is the map of America. I just want to focus on the two roles that I told about ISO. So if you look into the right map, I've highlighted a western grid where it is like a black bold portion of the map. This is called Western Electric Grid. There is a Texas electric interconnect, and there is this rest of the East. So one unique thing about American grid is it's not connected. So there is an Eastern grid, there is a Western grid, and there is a Texas. So if we are in short, we can't take power from Texas. We can't take power from New York, because there is a vast land in between, which is very like a desert. Having a transmission line from all the way from east to west or west to south, it's not economical. We're going to have a lot of losses, and it can be like $1 trillion project just to create, just to run down that transmission line. So they just cut it into 3 pieces. So if we have shortage in California, we can only rely on our neighbors. We can't go beyond this dotted line. So that's one of the constraints that we have. On the left graph, I want to highlight the reliability coordinator role. So reliability coordinator can be, so there are a lot of balancing authorities in the entire America. They're like definitely like hundreds. They could be hundreds. They all report to NERC. Their responsibility is that whatever area that they are responsible, that should get power at every point of time. It means we can't do load shedding, we can't have any outages, or even if there is a fire or an earthquake, we have to minimize the area where there is no power. So main reliability coordinator is they are highlighted with different colors. So the reliability coordinator has many BAs under them, like many balancing authority under them. So the one in green is what my company is responsible for, and there are 40 under our umbrella that every minute we have to make sure that everyone is getting electricity and it's reasonable. And if there is any planning in future, let's say there is an outage in a 500 kV line, then we have to plan for it. We do a lot of studies beforehand, and we will be prepared for it. We have to guide all the BAs in advance. So this is a little bit of history. This is all basic things that I talked about. I'm trying to build up some knowledge share that you have, that we go to the main problem. So let's start with renewables. You'll ask me why it's related to EV, but the policies that government has been creating from last 20 years, first impact was renewable, and second impact, which is not even fully there in our in our code, is EV. So the problem is same, the approaches are going to be same, but it's just going to be more intricate. So let's just briefly talk about what renewable is. As we know, we have conventional power plants, thermal and nuclear. They create a lot of pollution, and with global warming and all the policies that government is making, they want a power generation to be done from a resource where there is no pollution, from natural resources. The first natural resource is wind, where it's just like a fan kind of thing, turbine, wind comes, rotate it, and we're going to get some power from the turbine. One unique thing about wind, from my experience that I've got, is we have maximum wind during the night when I don't really need that much power. The load curve that I explained in the beginning, that that on average I need 8,000 less for the nights. And if you're giving me so much wind, what do I do with that? Then comes solar. Solar is exactly opposite. I'm going to have solar from morning 7 o'clock, maybe till evening 6 or 5 o'clock, but it peaks in the afternoon when my residential load is least, and maximum consumption is done in industrial load. So it's good. My biggest problem comes on a holiday, or it comes on a national holiday and weekends, where the industrial load is not there, but still a lot of solar is coming, and I don't know what to do with that, because unless I have a lot of batteries, I can't store this solar, and then it creates problem that I have to even shut down my my big other plants, so that I can handle the solar. So wind and solar is, we can't control when the wind is going to blow. We can't control when a cloud cover comes and all of a sudden solar just disappears. So I might be getting 10,000 megawatts of solar in the entire California, and cloud cover comes and I lose like 3,000 in just 15 minutes. And then it's very difficult for, especially like my job, to maintain the reliability at that time. And then also we don't know when it's going to come back. So the control over these resources is very, means it's impossible. And then it's coming as costly for the reliability operator. The next big problem is this rooftop solar. Around 2011, there was a policy, as I said, in California, that we're going to have rooftop solar. Every house which is built is going to have rooftop solar. So imagine from last some 10-15 years that all the houses are building, every house has a rooftop solar. So in summer, on afternoon day time, on like summer day and afternoon, most of the houses are actually generating enough that they don't even need any power from the grid. We have this net metering thing that we introduced when we had this policy, that how much electricity that house is actually getting from the grid, that must be measured. So we are at on a summer day, we have this negative net metering, that the house is generating so much that he is fulfilling his own need, like its own need, and also it's providing some to the grid, and grid has to give the money back. So that's all good if you are the owner of, that house. But then for a grid operator, it's very difficult to handle it, because I don't know how much you are generating, how much is your load. So the forecasting of a load that I do is erroneous, and it's very difficult. I can't go knock in every door and try to find out if your if your fridge is open, or if your washing machine is working, because those are heavy loads. If the washing machine is working during the daytime, I would like to account for it, because what if there is a similar house which doesn't have solar and is going to use that, and as a grid operator, I have to provide that much. So I think I'm getting too much into the details of that. Let's just move on to the battery. Now, given the problem of wind and solar in the rooftop, we had to invest in batteries. Right now, California has around, I think, 15,000 megawatt. Just in this summer, we have one plant which is around 250 megawatt plant, which is, I think, is the biggest in the world. We have to put these battery plants. Battery is very expensive, but to handle the problem of solar and wind and the that we can't the unreliability that the solar is creating, we have to have a battery. So some of the units are totally just batteries, and just this year in 2020, we have created a hybrid plant. So hybrid plant is nothing but a solar plant, and it has battery also. So when solar is too much, when it's generating a lot of power, it's going to give it to the grid and also charge its own battery. And when, let's say, a cloud cover comes, then instead of losing that whole output of the plant, the battery will come in and it will compensate for that much generation. So that's one of the innovation that we had in 2020 from our side, which we'll see in going forward how much it's helping, but that's the need of the hour, and we have to incorporate batteries now. So a little bit more on just the profile of how our life from last 10 years has changed. Mostly it used to be, as I said, coal, and then gas and nuclear. And as you see, slowly coal is going down. There was a mandate that we have to retire all our coal plant. We have already retired one big nuclear plant. We have only one nuclear plant remaining, which is 2,000 megawatt. The other one very big was, I think, 2013, we had to shut it down because of the policies of government. And now we have to shut down all the coal. So again, all the base power that we used to rely on nuclear and coal, and they will not be there, and we will have to live with solar and wind. Almost, I think, 50% by 2030, and we will be fully emission free, means all renewables by 2045, I think. So far so good. Are we still going fine? Any questions?
Okay, ma'am. We will take question and answer session at the end.
Okay. Okay, I will ask later. Thank you.
Okay, no problem. I will be keep tabbing Madhura, sorry, just to see that you guys didn't leave me.
Yeah, can I ask one question if you don't mind?
Yes, sir. Sure.
Yeah, see, in India also there is a net metering policy, and as you said, in America you are utilizing that net metering policy. How far the residential people are responding for it? One, whether all companies, distribution companies, are in profit. Second, and the third one is how you deal with gross metering type. For example, there are transformers and there are transformer losses when we are uh, exporting electricity from residential rooftop to the transformer. Then that delta, how do you manage? Thank you.
I didn't catch your name. What's your name?
I'm Avdut. Sorry, I'm Avdut Dikshit, and it was my question.
Okay. Hi, Abdul. So let me take the easy one first. Are all the utilities in profit? Yes, they are still in profit, and I think the profit margin could have been, changed because we have major three utilities in California: PG&E, Smart, San Diego, and for the LA. All of them are in profit. They are very small ones. Also, and I don't hear anything which is not like the utility which is not in profit. For the back and forth of the power, I think we have smart meters which are able to do that. Every house is equipped with that. So at least even if there is a loss, maybe it means that the rebate that the house owner is going to get is less. I personally didn't have the house which is constructed recently, so I was not getting any money, but I know my many of my colleagues, they actually make money in summers, but somehow means I didn't hear any problem specific to this. Do you have any follow-up question on that?
No, thank you. Because in India, we are facing now gross metering type of scenario, because distribution companies are getting lost due to the solar, and they are against it as their profit margin is getting lower. Of course, they are already bankrupted, but still, due to solar, they are not now in some more dire. Anyways, thank you very much.
Yeah, so when talking about bankruptcy in last 10 years, the only company which actually filed for bankruptcy is PG&E, but it was not due to involvement of solar or anything else. It was because there was a fire and government said that the fire is due to your equipment because the transformer burst or something. So that was the only reason. But profitability wise, I think I might be on a correct slide that I will talk about markets now, because I'm also up, like, as part of California, so we are also optimizing the generation and the load, which probably might be the answer that you might be looking for. So let me just jump right into the energy imbalance market that we created, and let's see if you get a better picture. So from last, I think 2014, we have this energy imbalance market. Like with all the policies that we were getting in California, it is getting difficult to have a reliability. And also, as I said, that we are restrained in the Western grid only. So we created this Western imbalance market. What does it mean? First of all, the normal market, as I said, that you have some generators and you have some loads. Every day before 10 o'clock, we get the bids, like share market bids, that which generator wants to participate. He wants to generate some electricity, and which loads, want to take it. So we run the optimization and then we have a result by 1 o'clock. Based on that, all the generator who are picked up, they buy the natural gas, and for next day they are ready. This whole setup was working good from last 10 years or so, till we started having a lot of renewables. Because it's only economical to generate and have contingency for 20% or so, like all the ancillary services that we're going to keep. We can't just, like load can't be 50,000 and then I have a capacity of 100,000. It means that you're just uneconomical, and you will be probably investing so much money that you might go in loss. So what smarter way California did was we created a pact with our neighbors, let's say Arizona, Nevada, Oregon, all these Western utilities. They came together and they have every 5-minute and 15-minute exchange option that if California is short, we can go get some power from Arizona. Normally also we can do imports and export, but it is not done, first of all, 15 and 5 minutes. It is done on hourly basis. And secondly, the cost to import and export used to be much higher. Right now, the electricity that I'm getting in my house, it clears at certain, certain dollars per 5 minutes. So same rate, I will probably get electricity from Arizona, and like for end user, there is no problem. For utilities, it is relief that they don't have to spend so much money just to have that extra cushion of 10-15% of contingency. So that is taken care of. Why this model is working from last like 5-6 years is due to the profile of Western grid. The northern part is quite green. We have a lot of hydropower sitting here, and the south part, Arizona and Nevada, we have a lot of solar here. So especially I think California is gaining a lot with this setup, because during the summer, if we have a problem, Arizona always have surplus in solar and we can always import from there. And during March or April, when we need power, there is a lot of hydro up there. Even we have Canadian British Columbia Grand Coulee plant is like one of the biggest in the whole world. It has so much power that Canada is surplus in power. They are just generating so much that they don't even need that much. So we can benefit from that. So this whole setup has been working very, very well from last 5 to 6 years. And I think this was my key project. So it's also, it's dear to me. Next, I'll go into the detail a little bit on what problems we are facing. As you can see in this curve, this wind is so much wind during the morning. When everyone is asleep, we don't need that much power. We have so much wind. Then we have a small dip here, and then we have a lot of solar. So our problem areas are this morning peak and this evening peak. We were okay like 3 years back when we had a lot of coal and we had natural gas, because we used to cover all this, dips with natural gas. And we used to always have coal running. So we were never short. We were over generating a little bit, probably. We can't curtail a solar or a wind, but we can export all the time. If there is because of the energy imbalance market that we created, if we really get surplus, our estimate, the forecast is not perfect, and we can, instead of shutting down a power plant, we can always export and someone else can use it. So now with coal going away and with natural gas going away, this morning and this evening is the biggest problem in sitting in control room for us. We have introduced some smart features. We're able to estimate the solar rooftop now. We didn't get any data, but then we just incorporated some artificial intelligence, and we started using that in our forecasting. That is working well from last 2 years, and we are able to at least forecast is better, so that we can use our hydro. So hydro is helping in these 2 times, and natural gas for now is helping. This is again another curve. So this is a very famous curve. I think it has become over the years that it's called duck curve. So like I said, that we have net metering. So this is a net load. This is not the total load. Total load is still pretty much flat, that we need that much energy. But since there is so much rooftop solar generated, we don't need that much. All those houses actually might be using electricity, but they don't need it from the grid. So this is getting deeper and deeper with years. So in 2020, it's almost like like the morning peak, the jump, it gets around 5,000 or 6,000 megawatt. So all of a sudden we have to, generate, and then all of a sudden we have to shut down. So hydro is coming handy. Battery hopefully will be our second best going forward. I think I don't want to take more on this anymore. Let's go to the real problem, that keeping the time into account. Let's look into the electrical vehicles now. So, like wind is a problem right now, solar is a problem, rooftop is a problem. And now we started introducing electrical vehicles. Electrical vehicles is nothing but, for me, it's just a load that which will need electricity at any given time, at any given point. So far, all these houses which were located, I could almost now, with so many years, we did some, learning, like, how you do in machine learning. We did learning where which house has that solar rooftop and what are the patterns of that. So we became intelligent on that. But then this electrical cars they're more volatile now. So let's just understand what electrical vehicles are, and then we'll incorporate all that knowledge in our grid reliability problem. So we've had hybrid cars for some time. We've had plugged-in charge cars. Hybrid car is nothing but like you have a normal car, like Prius is there, and you have a normal car and it has battery to start, or if you want to really rev up the car, you're going to use the battery. Plug-in charge car, that's also very famous in California these days, especially Chevy Volt is one of the top plug-in EV, where you do your run on electricity, but if you need, you have combustion engine also. The last and the most dangerous for me, the category is the battery electric cars, where it's only battery. Like, I think this picture shows the real, how the car would look like. It'll just have a battery. It'll not have all the combustion engine, normal mechanical combustion engine. It's going to run on battery, and periodically it's going to charge. So the biggest and the best battery EV right now we have is Tesla. It has a good range of around 300 miles per charge. There are more vehicles. I think there are bikes, and I even heard in India we have scooters. There are some airplanes which are manned or unmanned. NASA uses some airplanes just to collect some data, and then Boeing has an airplane, but they are not like really commercial. So it's just very minimal concern for us. There are some railways and buses. Buses are electric, but right now they're not like, we have a lot of buses which are electric in San Francisco, but they are actually all the time wired with the line going on top. So that's not a concern for the battery charging problem that we have. And just an interesting fact, there are some boats, and then Tesla also have trucks now. So trucks will probably need more battery, and we have to see when we have more trucks, how is it impacting. But so far, with all the given data we have, the battery electric cars are impacting a little bit, but also we have to understand that it's just like 5% of the total cars, as I said, 7 or 5. So it's not too bad. And we have very concentrated areas where there are, electric cars. So everything is manageable so far. So just fun fact, we have lead acid batteries and nickel metal batteries, and all these cars generally run on lithium ion battery. Tesla incorporated it, and I think it is working, fine for them so far. Now let's look into the data, like especially for California. Like I think in the whole America, California has the most number of EV vehicles. Thanks to the policies, every time you buy a car, you get almost 10,000, like 7 7,000 or something in the tax rebate from federal government, 2,000 or something state government gives, and they are giving very cheap electricity rates. As soon as you buy a car, you're going to get some $500 from your utilities. Every time when you're driving in in a traffic, you get a HOV lane. So there are a lot of incentives. So government is trying to push for people to buy electric car, because again, the same reason, they want carbon free, and they want less pollution on the roads. So they'll do whatever they can to incentivize people to buy the car. With the cars come charger. So we have more than 60,000 chargers. So I think I'll talk more in detail about the different type of chargers, but I think broadly we have 3 type of chargers. One is, just think of it as an extension cord in your house. It's level 1. It's famously called level 1 charger. Doesn't put too much load on the grid. It takes a long time to charge, so most of the people don't prefer it. Most preferred use, the way of charging is level 2 charging. It is that you're going to have a 240 volt charger in your house, where you will be charging. Most of the time people charge over the night, and that's why this time of use electricity rates come in picture, that from midnight to 6 a.m. electricity is very cheap, and that's where the government is trying to push people to charge their cars. That's also for a reliability perspective. It's not too much of a problem, because as I said, that there is so much wind at that time. Instead of pumping a hydro, means before these EV, what I used to do with all that hydro wind was, I used to pump up all my water back to my hydro plant, and with so much more wind coming, I can only pump so much. So good that we have electricity. It's actually helping me that people are charging, and we're able to use the excess wind that we used to have in the night. For reliability perspective, the level 3, which is famously called DC fast charging, that is the problem, because that's the ad hoc charging that people do, especially let's say for Tesla. It'll take you only 30 minutes to charge like 80% of your car, or like I think 60-70% of your car. So that's a lot of power given by the grid in a very short amount of time. So just to give you a rough estimate, a car, when it's charged, it takes almost 4 times the load of a house. So if you're charging the whole car in 30 minutes, that's a lot of power for any nodal point also, and in terms of the power also. One more problem for the reliability that we have is that it's very concentrated in only few areas. Only big cities, let's say San Francisco and Los Angeles, will have almost like 80% of the vehicles. That's where most of the chargers are also, rightly located. But that is adding the load. San Francisco and LA is already very heavily, dense cities, and now it'll have an added EV load also, which is going to be variable. One good thing, which I think government policy is helping us, is that most of the car owners also have rooftops. So for the level 2 charging, it can be either in the house, or it can be in the offices or like malls. So there are a lot of offices which give either free charging port to your car, or very low rate incentivized charging. So that is also helping, because in the daytime we have a lot of solar. So if someone is charging when they go to office, and when they come back, they stop charging, it is actually helping us, because we're going to have that excess solar. We're going to flattening the curve. All those bumps that we saw in our load profile, they will flatten out. So far so good. But then in some, I think 20 years or so, we're going to have more and more cars, and we are probably going to have same kind of concentration on the car. So we have to prepare for it. So I think going forward, I'll show you, what are the steps that utilities and ISOs are taking. Just fun fact on the electric cars. As I said, there is no GHG emission. Normal car will have 25%. So all that global warming is, the GHG is blamed for that. So that's why government is pushing for EV vehicles, that EV doesn't have any GHG emission. There is no pollution because there is no carbon dioxide. Normally, you're going to have that, just I think as a mechanical engineer, someone will understand that normally when you have a normal combustion engine, you are not utilizing all that. Most of that gets, the energy gets wasted. But for an electrical vehicle, we are actually using a lot of power. So all that battery charge, and then what we use is almost 60%. Good consumption is done. Why it's popular for the end user, apart from all the incentives that government is giving, it's also very economical to use. So there are some expensive cars in the market, like Tesla is there, and then I think Porsche is there, but there are very economical cars. Personally, my friends lease them around $100 per month. They just lease, and then they just charge in the offices for free. So imagine there is no expense for a car going back and forth from the office to home. That car works very well. They don't need a long range car. So many people naturally, to save money, they are choosing EVs nowadays. Now let's focus more on California because that's the case study that we're doing. On the whole, for America, we have maximum concentration of the electric cars in California. Around 45% of the whole American cars are in California. And I think there is a new law which is recently passed by California governor, that after 2035, he will ban any non-EV car, any combustion engine car. So they can still be on road maybe for a couple of years further, but then there will not be any sale of that car. So as you can see in the right graph, that I'm saying that anyways, with all the incentives, the growth is, the sale of the EV is rising, but then after 2035, it will sharply shoot up. California also has the Tesla plant located there. So as I think some people will know that there is no showroom that you can go and buy Tesla. You just need to order it online, and they're going to ship it to you to the nearest Tesla station. So when these cars, especially Model 3 was announced, maximum cars were shipped to California. So naturally, just by having that factory located in California, a lot of people got cars faster. So other part of the world got it, 1 or 2 years later. So just for that purposes, we have more EVs than anywhere in the world, which is fun. Means it's of a pride, but then also we face the challenges much before than anywhere in the world, so we can't really learn from anyone else, but I think other people can learn from how we handle the surge of EVs. I think let's go into details of charging now. As I said, level 1, 2, and 3. Level 1, very minimal. Not many people prefer that. Level 2 is very, 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 prominent these days. Workplaces and residential charging. It costs also to some of the people, not too much, but just $1 or $2 per hour. On contrary, level 3 is more expensive. Like every minute you have to pay $50 or so, but in 30 minutes you're going to get the car charged. So anyone who doesn't have a charger in the house or has a facility of a office which is providing this feature, they generally rely on this. So as a state and as utilities, our main focus is that we have to minimize this level 3. We have to encourage people to go to level 2. So many of the utilities, like I said, that they even give you, as soon as you buy electrical vehicle, they give you $500 or $600 straight. They are trying to encourage you. That is when you have the charging in the house. So they are giving you some money so that you can, put up a charger in the house. They're giving you very good rates, least expensive, that you can charge your car from midnight to 6 a.m. So government is helping there, that they are, they're encouraging people to go to level 2. But then still, level 3 is rising up as the EV concentration is rising, and then we have to see how it will impact in future when we have like 100% of the EV. Just to give you a rough idea on what is the time of the day that people are charging. As I said, like level 2 is still 70% of the people charge by level 2. And if I can run you down through the hour, midnight people are charging through level 2. Around 8 a.m., that's where we see a surge on level 1 or level 3. So maximum level 3, the fast DC charging, happens from 8 a.m. to around 6 p.m. I think grid is ready for them to take that much power right now, especially during the sun is out. As I explained, main problem is around 6 o'clock when the solar starts going down. We have to discourage people to go for fast charging at this time. Other than that, solar is ample in our state that they can benefit the fast charging during the peak solar time. But then we have to discourage only in the morning peak time and the evening peak time, so that we don't have any reliability issues. One more problem I want to emphasize here is that for a reliability, for power reliability, we have congestion in the system variable to the load. So if we imagine the California, let me go back to that slide. So if we imagine the California graph here, so San Francisco is, in north and LA is in south. We have few points where we called the connection points in our grid. Like every house is a connection point, but we don't measure our load balance at every point. So there are a lot of points, and then there are aggregate points, and then there are some pricing points. So if there are some 50,000 points that we have defined in our map that we're going to call our pricing point, they can be 3 times the aggregate point. And as an ISO, we monitor all those points. Points can be just like, like 20 house put together. The transformer which is serving to that can be 1 point to us in our database. So we are monitoring what is the congestion, how much is the load, did the load surge all of a sudden, like, it became 200%, then we have ways, and within like 7 minutes we can turn up a new plant and provide more power. This is market. But then for energy balance system, every 4 seconds we get the data from our field that we have around few percentage fluctuation. We can handle all that. So over the time, we know which points are our problematic point, where the most congestion is there. Congestion means that my either power line is overloaded, or my let's say generation shortage is there, and load is too much, or there is too much generation and there is not enough load. So we have studied all that and we have corrected our model. If there is a need to install a new plant, we have installed it. If there is a need to install a new power line, we have installed it. So over time, we smoothened it out and we try to make the whole system, the power flow smoothly so that there is no congestion. With the EV, now let me go back to this chart where I'm showing you this fast charging. With this EV, it's not stable. It's not that car, that one particular Tesla Model 3 will charge in that station all the time. People are on the long trips when they're going, and that's where they do the fast charging most of the time. They're on the go. So we can't predict where that car will be fast charging and how much, because sometimes they just top up to 20%, sometimes they go and charge all the way to like 80% or even 100% because they're long trips. So that's the variability, that first of all location, and secondly this how much amount of power they want. So if a EV today gets, let's say right now gets plugged in, so what is my expectation? Do I turn on a plant, or I just try to just change a configuration here? For how long this EV will be charging, nobody is telling me. So there is no forecast available right now to predict this. Right now it's very small amount, so we have that much capability to move. Every 4 seconds we get a signal, and we have around 5-10% that we can move in our power system, so it's not a problem. But then if we have all the cars just doing this, then it's going to be challenging for the grid reliability. So is it good so far? Are we doing good? Shreyas, are we still there?
Yes, madam, no problem.
Okay. So let me go more into the intricacies of charging. As I said, the charging behavior. We have studied how much people, at what time people are charging and what are the peaks of the charging. So there is a pattern and studies done that we see that the maximum load that we have seen is either 6 a.m. People wake up, they plug in their charge, 6 a.m. is the peak. Then we have 5:30 p.m. That's where people come home. They come home, they just plug in their car and they start charging. And we have 8 p.m. So 8 p.m. is unique because all the utilities which are giving these incentives, some of them have 12 to 6. That's the lowest tier. Like that's where it's going to be very cheap. Then there is another tier which is from 8 p.m. to midnight. So there are some cars right now, let's say Tesla is an example, that you can plan. Like you can just tell the car that what time the charging should start, for how much percentage the charge should go on, and then stop. And at what time you have to stop. Not all the cars are intelligent enough. You can't program them like that. So 8 p.m. is where the tier 2 electricity rate starts, and that's where we have seen that most of the cars gets charged, and it can be very well at EV volt, because EV volt you have to just plug in. You can't program it. So these are the 3 points that we have noticed. So 8 p.m. is beyond the peak time. As I said, that solar is already out of the picture. At 6 o'clock, we have our base load up. Maybe a natural gas power plant is already up. So we can handle 6 a.m. Almost handle 6 a.m. We can handle 8 p.m. The biggest problem right now is the 5:30 p.m. because that's when most of the time solar will be going down. We don't want any extra load to come in at that time, because whatever the load is, we're trying to manage with hydro and the battery that much. We don't want any more EVs, especially the DC fast charging, to happen at that time. So there is a lot of policies going around this, that what time we have to incentivize people, and also put penalty on people. So this 530 will be probably as a penalty that instead of getting any rebate, you will be probably paying 3 times, just to discourage people not to charge at that time. There is another problem that we have seen is this clustered charging. That's the term, formal term. But what exactly it means is if you have multiple cars of the same owner at the same transformer, it puts a risk of overloading that, because as I said, 1 car is equal to 4 house load. So if you put 2-3 cars, then it's a lot of electricity to be taken from that transformer, and it can overload. So over the time, you can have you can either damage the transformer over the time, or you can definitely reduce the life. You can have a local outage in that area, or you can just in the worst case, you can have a failure of that equipment. This is, I would say, it's not a big deal right now, so there is no policy that we are creating, but there is also a lot of work going on for the metering part, just to discourage this. But right now, at least in my knowledge, we are not working too much in this area. Main work is the behavioral part, where we are trying to incentivize and penalize the owner. Then I think I just want to emphasize again, we are trying to reduce this fast charging. We want to encourage L2 and we want to discourage L3, the fast charging. Then let's get a little bit deeper on what tools we have right now that we can play around, and we can handle the situation with the limited EVs that we have. As I said, not a big problem, but for EVs, I would say not only for EVs, but also for other reliability issues. We are California government. They have decided that they have to rely on battery. Last August, we had a very unfortunate event that in August we were 4,000 megawatt short. So it was so hot, and it's a COVID year. Like normally from last so many years, we know when people are at home, when they are in office, when the industry is on, we have a demand response contracts with the industry. They are the big loads. Commercial buildings are big load, and industry, any factory or something is a very big load. So we wrote contracts with them that anytime if the consumption is too much, that we are not able to meet our generation. So we have enough capacity, but it's also a matter of time that in 30 minutes I will be able to meet that load or not. So if we see that we will not be able to do that, then we tell those industries to just shut down. It comes with a cost. We have to pay them a lot in advance, to be able to shut down. But then at least that's the way that we escape any load shedding or any important businesses. If we just let shed the load, then we just shed the whole area or a whole community. So there we can't pick and choose. So there are some industries, they signed off with ISOs that if you tell us, we will be able to shut down. You just give me so much money and I will comply. Within 5 minutes, I can just shut down. So we've used demand response from last 5 years very well. But this year, especially 2020, we had COVID. Not a lot of offices were on, but they were on enough that they were using all the electricity and everything, because in July or August, we had optional offices on. This is the unique year that we had a lot of residential load, because normally the residential load is very high in the morning and the evening, but during the day we don't have all the laptops logged in, we don't have all AC on, and those were the time that it's very hot and all the ACs are on in the house. So we had extra residential load, we had extra commercial load, like normal commercial load and extra residential load, that affected in a 4,000 megawatt extra energy requirement, which we didn't have that time. And it was an unfortunate event that we had the whole Western, grid. Nobody could export to anyone. So all that energy imbalance, project that we did so that we can rely on our neighbors, that also didn't work. So we had to do the shutdown. So this is, I think, after 20 years that we had to do load shedding. But the impact of that is that we will eventually probably will have tens and thousands of battery, although it's going to be very expensive. But within 1 year, there is a mandate from California governor that we have to have around 1,500 megawatt by next August. That's exactly 1 year after, the problem happened, and August is the time that we have very hot days in California. So that's one thing. But then one good thing what this policy will do to us for EVs, that any time that we have any surges due to the fast charging, this battery will come in handy. I think in summers, sometimes I was involved in this 230 megawatt power plant that we just started, and I think it was in papers that it's the biggest in the whole world. So we created a need of having so much battery power plants because we have so much solar and wind in our grid. And as I said, the time of the day rate, we are giving good rates so that from midnight to 6 a.m. it's very cheap, and there is some discussion to tell the end user to not do any charging around 5:30, means 5 to 6 o'clock, if possible. We don't have a way right now to communicate straight to the end user. That is something which we will see in future. But right now, at least notice can be sent to all the users that we are short. It is an email form which every ISO gives to all the utilities, and utility sends it out. It can be a text message or an email. Every person who is connected to the grid gets a message that if you can shut down, please shut down. In last 2 or 3 years, there is a program that we did, means not the ISO did, but there is one of the companies, they just ask people to join in, and if you shut down for that 1 hour, you even will get some money. So people actually made some $1,000 a month just by complying the demand response. So we are not only penalizing our customers, we are also working on our infrastructure. As I said, we do a lot of study on our congestion management, and we try to we try to incorporate anything that a power plant or a line, if it has to be installed, it will be installed so that we can provide the power at any point of time. But that takes time, minimum like 1 or 2 years it'll take to build up infrastructure. So the fastest way is to take help from the customer. Now I think it's my favorite slide, and it's very futuristic, and we have to see where the world will go. But I'm doing research in one of these future technologies, which is the smart EV charging. I'll run down all the efforts across the world, what people are doing, so that all the utilities and grid operators will be ready when we have 100% EV, that we don't need to put limitations on any customer at any point of time. Also, we can take help, means instead of becoming a problem, it can actually help us. So that's the whole aim going in future. We have to see how the world unfolds, but I'll run down on all the projects which are going across the world. So one is the dynamic pricing scheme. So as I said, the demand response, you just get an email that please shut down the power if you can. But there is a customer incentive program which governments and utilities are trying to incorporate, that there should be different pricings for different car. Like if I am the car and I'm going to San Francisco Folsom Road at 5:30, I will get a different charge. But same charging, if I go at 6:30, it will be different. And I know it beforehand how much I'll have to pay. In the app, I don't even have to go to the charging station. I'll have an app. I like how we have petrol pumps everywhere. Someone gives an expensive gas, somebody gives an cheaper gas. So that's the futuristic plan, that on the map you should be able to know where the charger is empty and where is the cheapest. So logically, the cheapest will be where there is a surplus in generation, and it will be expensive when there is a lot of congestion. So we want to make the user intelligent, and we want to give all the information to the user so that they can pick and choose. Then there is this one interesting project going on. This is the vehicle to grid. I think it's very much in news. I haven't heard anyone actually using it. If you guys know which is any project which is going on, I would love to learn about this, where the car is not only taking the power from the grid, but it's also giving back. Like then it's nothing but like an inverter in our house, that when the electricity is cheap, I charge my car, and when it's expensive, if I give you a message, then you just become an ad hoc generator. Whatever in the capacity that you can do, you can give it back to the grid, you can give it back to your house or the whole building. So that's an interesting project going on. Then on the manufacturing side, there is a lot of research going on the long-range batteries. I don't know how helpful it is going to be, but the intention there is, because the longest range battery right now is from Tesla, like Model 3, that we can only run 350 miles per charge. So if we can increase that, then there is no need of ad hoc charging. We can do our whatever the trip, 8 hours or 10 hours of drive without even charging at once. So we can charge in the night and then again drive the whole day and then charge in the night. Then again, of course, the responsibility goes to the customer, but then he will have an ability to do that if the range is big. I think this year or last year there was a paper on solid state batteries, which are promising, and we have to see how it comes out. The next is the intelligent charging. As I said, there will be a cloud-based application, and then the data will be available, and then we can have the charging station and the user, everyone will be connected. How a Google Map is there, you'll know exactly which charger and how much is the electricity. I think if that is possible, I see challenges there. I'm working towards smart EV charging. The problem is all these players. It's a very regulated industry. We can't really share any knowledge, any data with anyone else because everything is so regulated. So we will see how it comes. The government has a big role to play. But then if this is done, the smart EV charging is possible, then I think with the intelligent customer, we can actually boost the generation instead of being a burden on the grid. The next is, it's a very interesting concept, the virtual power plant. They're nothing but just, all the distributed energy resources put together. There is no like a power plant. It's just all these distributed energy resources put together. I think there is a project that GE is initiating. Maybe in 1 or 2 years, we have to see this is going to be the first virtual power plant of the world, and we have to see how it plays out. And if it's a success, I'm sure more and more people would like to do that. I personally don't really, I don't get excited on this because if I have the power of smart EV charging, then why do I even need this virtual power plant? Because after all, if I have a car that I can do V2G, the vehicle to grid, and I have the app and the cloud base, all the database, why do I even need a power plant? I am my own power plant. I'm gonna have solar. If solar is not there, I have my EV. I can always power my house. For at least individual EV owner, I don't know how much it will be useful. Of course, for commercial and industrial, we can see some use. Then we have this behind the meter storage. It is very it's a very I think people are thinking it's a very unique thing, but I know in India we always used to have inverters, which we use it from 20-30 years. So this should not be very difficult to implement. I think beyond that, just to come back from.
Good morning. Am I audible?
Yes. Hello.
Can you hear me?
Yes. Hello.
Yes, Karandikar sir. Karandikar.
Okay. I think I'm on my last slide. Let me just finish and then we can talk. I think I'll just wrap up in coming back from all the technical and detailing that we looked into the grid and the challenges and all. In the end, we need EVs because of the pollution. It's not going to create any pollution, so it's something that is inevitable. We're going to have it. The responsibility as reliability or anyone is to use it in the most efficient way, and that's where me and my industry is working towards. We are trying to flatten the curve using the EV instead of EV becoming burden on us. I think I'll just wrap up with the thank you, and if anyone has a discussion or a question, I'm open for that.
Yes, participants, if you have any questions, please unmute yourself and ask.
Yeah, thank you very much, Rekha ma'am, for giving this fantastic webinar. I have one question now. I'm Avdhut, of course. Due to EV, how much electrical load will get increased? For example, nowadays you must be having 1200 gigawatt installed capacity. Till 2035, what are your expectations? How the projections will go ahead?
So for the forecasting, I would say that by 2030 or 2040, 30% increase we are projecting just due to the EV charging.
Okay, great. Thank you. Thank you.
Am I audible?
Yes, sir.
This is Dr. Gaikwad. Rekha madam, the presentation was really very good. We understood a lot of aspect apart from this in this technical domain. I would like to ask that in the Indian scenario, can you suggest the solutions that we can start up with the things going on? You must have studied, you are knowing the things, what are the challenges in the Indian scenario. So would you like to suggest a few points from your end? Because you have studied the different countries' utility problems and sort of the things. So how would you give the solution for the Indian utilities and the Indian customers and the Indian industry to go with this particular coming domain? Thank you, madam.
Okay,
Please, madam.
Hi, Mr. Gaikwad. I think interesting question. I may not be the best person to, forecast Indian market because I personally don't know the data. Once the data, probably if I see the data, I will be able to answer better. But I think from my personal experience when I was a kid, how I saw the electricity grid at that time, I think in India lately there is a surge of solar, which is a good thing. But then you're going to see the same kind of problems that we saw in California, that the sun comes only during the daytime. So there might be a point that you might need batteries. One disadvantage of Indian grid is I don't think we have too much hydro available. There might be some government policies like we have in America that if we put hydro plant, then fishes will die or something. So lately we are not actually producing too much hydro. Otherwise, we have so many rivers in India. If we can put in some effort in hydro, so that as solar is going up, when you're going to have that morning peak and evening peak, and then all of a sudden you're going to see a downturn, then you need something to compensate at that time. Battery is very expensive. Honestly, for us, it was very unfortunate in August that we had to deal with that situation. So we are investing in batteries right now. The best would be if you can use the EV as those batteries, because I think California was some 10, 20 years ahead of the rest of the world. So we saw this problem. But if EVs were already here, imagine I have 100% EVs, then whenever I need, and the good thing is software, if once developed, everyone can use it. So if you have a software where you can tell an Indian customer that at this time, if you charge, I'm going to give you 100 rupees per minute. I'm sure in India, so many people are going to charge. So you're not going to see that problem. So I think my experience is always balancing it. You have a lot of solar for sure. I don't know about wind. I know in Chennai there is a lot of wind, but I don't know about other part of the India. Mainly, we can rely on solar, and we have to incorporate either hydro or batteries to compensate. Otherwise, solar is very fidgety. Personally, it's not my favorite, but we have to live with it. I have one follow-up question on the policies of Indian government. Is there any mandate that government has said that, beyond that point, the whole energy should be like 100% renewable or something? Do you have any constraint like that?
No, madam. Recently, what we have tried to understand that the 40% of the overall generation should be from the renewables. They have not made it, or I don't know, possibly that how much should be from wind and solar and from the other resources. But from the overall utility, whatever is generating the energy, the 40% should be contribution from renewable energy.
Okay. So honestly, right now I'm already at 40. So far, it was good. The good thing is per house, Indian customer is, I would say, a little bit more intelligent. If you ask them to shut down AC, they will shut down AC. Because if I tell American customer to shut down AC, they don't shut down AC. So, it's also customer base is more intelligent, more flexible. So I think you should be fine going forward. Just keep up the hydro and keep up the batteries as a contingency. Otherwise, till 40% we are okay. Till even 50% we are okay. The problem comes when we are 100%.
Thank you, madam. Fair enough.
Any more questions from participant side?
Okay. May I ask you one question, madam?
Sure.
You mentioned about the congestion management because of EV, because EV charging is a surge, which is coming to the grid, and the location is not fixed. Also, the time of day is not fixed. That is one challenge which you need to look after. But the second challenge, if we consider renewables in the grid, integration of renewables in the grid, like wind. So wind is also very uncertain source. So how would you look to this? Because there are then two challenges for congestion management.
So let me just emphasize on the nature. So wind is a generation and EV is a load. So let's say I am in a situation that I have too much wind. So of course there won't be any congestion. The second thing is when I have too less wind, and then that's when my hydro comes in and my battery comes in. In totality, I should be able to provide the electricity to my end load, right? The congestion piece comes in on the transmission line that, from generator A going to load 1. If there is a line and then instead of generator A, I'm using generator B, I use a different line. And then I have to optimize that. So I think we've been living with it. We haven't seen any problem because of wind being uncertain on congestion too much, because we also have I think there is like when I run my market, I run on pricing run, and then I run on the optimization, on the congestion. So every time I'm gonna say, okay, generator 1, 2, 3, 4, they come online, and then I'm gonna check if they come online, what is my congestion, and if it's too congested, then I'm gonna change my generator. So I do this back and forth 3 times, and then I send out my result out to the generators. So in that every 5 minutes, like I think I explained that it takes me 1 minute to do that optimization, that going back and forth, I do my scheduling run, then I do my power flow, run the power flow, make sure that there is nothing is congested, do it again, because some of the generators will change based on the congestion. So I think we have been successful so far with this optimization, putting constraints on congestion, that if it's more than 100%, the line is loaded more than 100%, just don't take that part, take something else. So I will always have other generators other than that generator B to serve my load, so that line 1 is not loaded. Is it clear? I think it's much easier if I draw all this, but in short, we are able to handle the problem with the wind fluctuation. The problem with the EV, what I wanted to emphasize is that my load so far was always stationary and variable. Okay. Now this EV is not stationary. It can be anywhere. Like this house can be anywhere in the map, and it might be asking me to give anything. Like houses are also like that. Like if you look into our house, sometimes we watch TV, sometimes we don't watch TV. Sometimes we run our washing machine, sometimes you don't run our washing machine. So every time you turn on the appliance, you are adding a load. So in totality, you might be asking me certain amount of megawatt. But over the time, we have created a load profile that it's a pattern that we have learned from it. Looking at the past behavior of the customer, we know how much he's going to ask. So I think we have become intelligent enough to forecast the load. With the EV, that machine learning has not happened. We don't have enough data and pattern to estimate for it. So the I would say the variability is too high right now. I think over the time it might be better.
Thank you, madam.
Okay, so let's conclude the session. So I would like to thank Ms. Rekha Sharma for enlightening us with her knowledge. It gave us a deep insights into the topics like electricity imbalance market, more integration of the renewables, the curve, various government policies for EV were discussed, and how EV impact on the grid reliability, congestion problems and solutions with EV were also elaborated. It's a nice experience for us to know the California case study. We got this opportunity to know how you are operating and managing the entire California grid, considering all constraints. Examples you covered are also very informative. We really got a feel that we are monitoring a California grid with you. all the problems grid facing by by integrating the renewables, their solutions and the challenges faced, and the integration of the EV, all those issues you discussed in the depth. So thank you very much, ma'am, for giving us this opportunity.
Yeah. Thank you. Good night.
So I'm
Good.
pretty sure that the knowledge you shared will definitely help us. Once again, I would like to thank you for taking out time from your busy schedule and enlightening us with your knowledge. Thank you very much, ma'am.
Thank you. Bye-bye.
Bye bye. And thank you all participants for your active participation. So our next session will start at 12 o'clock. Thank you very much.